Alrighty, thank you all for coming. I just want to preface this with something completely unrelated, but I sure as shit want a knitting talk. So Sarah, please. And I'm excited to discuss this with you later. So I study sleep in flatworms. So this is a little flatworm here. Do I have a pointer? I do. They're actually only about 1 centimetre, despite what it looks like on stage. But I'm going to go through a couple of things first before we get into it. So first of all, some acknowledgements, just because it's always nice to thank people. So my supervisory team at La Trobe, where I did my PhD, and then my volunteers and collaborators over here, as well as the Defence Science Institute, who basically paid for me to live throughout this PhD, so that's very kind of them. Okay, so what is sleep? So I'm sure we all know kind of what sleep is on a level of I do it every night, hopefully. But we do have some criteria here. So mainly it's a period of unconsciousness, but we have to get a bit more specific than that because so is sedation. So we have some behavioural criteria. So when we're looking at things, one of the first questions I always get is, how do you know the worms are sleeping? And this is how I know that the worms are sleeping. So we've got some behavioural criteria. So we have a circadian organisation. So I'm just trying to get out the way. So we have nighttime, daytime, and we usually divide these up into sleeping, working, play, eat, those types of things. We have species-specific posture or location. So shout out to my cat Sparkplug, who is the model for this. He's a beautiful little boy. We also have rapid reversibility. So this is not my duck. I found this online. But you can see that this duck is falling asleep, or trying to, and then rapidly coming out of it. We also have an increased arousal threshold. So this is the one I always like to explain. So if I came up to any one of you at this moment, hopefully you're not sleeping, and I poked you in the arm, you'd look at me like, why are you touching me? That's perfectly fine. It's a normal response. Not everyone likes to be touched. However, if you were sleeping and I came up to you and I poked you to the same degree, unless you're a super light sleeper, you probably wouldn't know that I was there. So I'd have to punch you to get awake. And that's what this little husky is doing to his poor, poor owner there. So an increased arousal threshold, it takes a bigger stimulus to wake you up once you're asleep. And then we have homeostatic regulation. So of the same vein, if you normally get up at 8 a.m. and I woke you up at 5 a.m. by punching you, you're pretty pissed off. And then I continuously punch you for the next 3 hours until you have to wake up. I'm running away at this point because you're real mad, but you're going to stay up that whole day. And then that night you'll either go to sleep earlier because you're really tired, or when you eventually go to sleep at your normal bedtime, you're going to sleep more intensely. And that's what we call a homeostatic regulation of that sleep. So these are the 5 behavioural criteria that you use to discover sleep in something super small or weird. Now, if you're not small or weird, this is what we'll use. It's an electrophysiological criteria, and this is probably what you think of when you think of sleep. It's the electrodes on the face, on the body, on the head. Doesn't help you sleep at all. But we look at the electrical charge of the brain and the differences in electrical charge between regions of the brain. And that's how we figure out if you're asleep or not. So here we have a mouse. And this is what the mouse brain, it is different between species. This is what a mouse brain looks like when it's awake. We have non-REM sleep, and I'll go through this in a moment. Non-REM sleep in a mouse, you can see the electrical activity there is quite different. And then we have REM sleep. Now this is where it gets fun, trying to analyse this, is because REM sleep looks a lot like awake. So we often call it paradoxical asleep because your brain looks awake, but you're actually paralysed while you're engaging in this. So let's have a look at REM and non-REM. So REM is rapid eye movement sleep. So we have 2 categories, REM and non-REM. Non-REM sleep is sleep before you get to REM. So there's 3 different stages there and really distinct brain waves like we saw in that mouse, or we can see in that mouse. Now, REM sleep is typically the dreaming sleep, so your body becomes paralysed, but your eyes move a lot, and your body becomes paralysed so you don't get into fistfights with your partner or a housemate when you fall asleep and you're dreaming of getting into a fight with someone. Okay, so let's talk about the evolutionary longevity of sleep. So we have chordata here, if you remember our question from trivia earlier about what is a chordate. Chordates, they have a spine. We then break down into other different types of taxa. So the highlighted ones in green are taxa that we've studied for sleep. So these animals have actually all shown to engage in sleep of some kind. Now, it's not the same kind of sleep across all these different species, but they do have distinct sleep and wake states. Try not to spill my beer. What I did was find it in this little guy here. Now, I do call it a little guy for no reason. They do not have a gender, but I call them my little wormy boys. So we're going to deal with that tonight. So they're small. They're about 1 centimetre long, really, really small. They're freshwater aquatic worms, so they're not earthworms like people think they are. They're bilaterally symmetrical. So what I mean by that is if you cut this worm down the centre between the eyes, it's the same on either side. If we have a look down, whoops, where's my pointy? If we have a look down here at the Nidaria, that is a radial symmetrical animal. So no matter where you cut it, you're going to end up with sort of different sections. It has a really simple brain, and I'm going to show a photo of that in the next slide. And as far as we know, it only has two states, active and inactive. And that's what I'm actually showing here, maybe if you can see. A big active worm and a squishy little asleep worm or inactive worm. So why do we care about these, right? They're a tiny little worm. Who gives a shit? Well, this image here is why we give a shit. So this green spiky thing is the flatworm's brain. And now one of the reasons why flatworms are really cool is because their brain is divided into 2 halves. You might remember that our brain is divided into 2 halves. It's one of the only invertebrates where this is the case. Things like other worms, fruit flies, I can't think of a single other invertebrate, but those 2, they have what we call like a mushroom body brain. It looks very different to a human brain. So what researchers have said, this is more similar to that of a vertebrate brain than of other invertebrate brains. So that's reason number 1 why they're awesome to study. Reason number 2 is this bad boy here. They regenerate. So this worm here doesn't have a body because I cut it off. And so fun. This flatworm will regrow into a full flatworm. So it's going to regrow its butt to look normal, but its butt that I cut off is also going to regrow a head. Yeah, that's the wow factor. It's the reason I'm standing here today. That is the coolest part about these flatworms. So let's have a look. Now, I know my figures are a bit awkward and uncomfortable to look at. This is just going through some of the criteria that I talked about, those behavioural criteria. So what we can see here, the black bars are nighttime and the not black bars, so here, is daytime. So we can see that the animals are inactive during the day, and I have 3 day periods, and they are active at night with a little snoozy time about here. So they're circadian organised. That's our first criteria done. It was very exciting when this graph came out this way. What we also did was see if this persists in constant darkness. So even in the absence, of light, they still follow that same rhythm, which is super important because it means that there are other factors involved in their sleep. I'm so sorry. So this one, my uploads didn't save and this graph did look a lot different, and I'm so sorry. So we wanted to check that homeostatic regulation. So I woke up my worms 3 hours early and I kept them awake for 3 hours, and then I let them go about their day. So the way that I did this, they're very small, remember, is I sucked them up out of their water using a little syringe, and then I squirted them back into their water. And they're not super pleased when you do this to them, so they'd like wobble around for a little while, and then the moment they stopped, I'd do it again. I'm so glad that they're so small and need water to survive, because I would not have done well if they weren't. So I did that to these poor things, and that's what this is showing here. So I made them be really active at this time period when they normally would not do anything. And what we can see is in these open circles that their activity actually decreases a lot compared to normal once I've done that to them. So we've showed that homeostatic regulation. So they are sleeping longer than normal, and they may or may not be sleeping deeper than normal. So it's really cool because you can find these things out while doing a, mainly in uninvasive study over them. So the next thing, of course, is I wanted to drug them because now I know they sleep, so why not give them something to help? So I took some of this image is from another paper, this section of it, and we can see that these neurotransmitters either keep animals awake or asleep. So in the mouse, you've got awake and asleep. In a zebrafish, you have awake and asleep. Fruit fly, it starts to change up a little bit. And then in the flatworm, we didn't know. We had no clue what it was going to do. And that was my goal, to find out. So I drugged them in a really strange way. Instead of just injecting them with something, they don't like metal, so they often disintegrate if you inject them with... It's the only way to kill them. If they touch metal, they disintegrate, so I couldn't inject them. So already I was having a struggle. I gave them a bath in their chosen concentration of their chosen drug, and by their chosen I mean mine. But I also fed them. So I feed them hard-boiled egg yolk, and I dyed it black because you can see it. And I also drugged the egg yolk. So these poor things kind of got... No, I won't say that. They got drugged and bathed against their will, I guess, so that I could see what they were going to do. And this is how we told the difference. So this is a non-drugged worm and this is a drugged worm. There's quite a big difference between them there. So it was obvious to see when they had actually taken up that drug. And this is what I found. So as well as adding the flatworms, I did some deeper research to see what jellyfish were doing, because a lot of people have started looking at the jellyfish as well, because they don't have a brain as such. So people are super interested in that. So the grey circles are where I got nothing, and the yellow circles are where I was able to keep them awake for longer than they normally would. And the blue circle, just the one, unfortunately, is one that I managed to induce sleep in. And again, I'm sure you're like, all right, cool, why the fuck do I care? Well, we care because if you have a sleep problem or a waking problem, and if it's really hard to diagnose, it's really hard to treat, if we can figure out what the evolutionary implications or the evolutionary starting point of sleep is, we might be able to target new drugs and new receptors in the brain to try and actually fix that. So what this image actually says is that dopamine, histamine, and GABA have been around for many hundreds of millions of years. So my flatworms are 800 million years old. That's when they first appeared in the timeline. The jellyfish are even older, and these receptors have carried out their same functions. They've probably picked up a couple of others along the way, but they have a base function of helping sleep or wake, which is really exciting because that's super old. And hopefully will lead to some really cool drug therapies at some point when people hear more about the flatworms. All right, so this is the funnest study I did, so I've left it for last. I decapitated a bunch of flatworms. So I have my whole flatworm here, which is also this image, and I recorded its activity. I then cut its head off, and I ended up with two different individuals, okay? And this is where the stats got really tricky. So I have a head and I have a tail. Now, after about 16 days, both of these regenerated into relatively whole animals. Now, cohort B, and yes, cohort B is on top because I didn't look at it as closely. Cohort B is not the aim of this study, this one was, is smaller. And what we think is because when we cut it, it doesn't have a stomach. Its mouth is actually down here. And so this individual was unable to intake food. So we think the regeneration process was slower in it. So that's why it's a little shorty boy. So this one completely regenerated those goofy eye spots as well as its entire brain structure, which is awesome. If only we could do that. This is the only animal in the world where you can cut its head off and it is happy for that to happen. It will go about its daily business for the most part. So what we see, cohort A, so this is the one that lost its head. That's our baseline activity. Unsurprisingly, without a head, it doesn't move much. Once it regrew its head, it did sort of increase its activity again, but not a whole lot, significantly, but not a whole lot. And that was at night time. And then during the day, we had very similar levels of activity because remember, these animals are nocturnal, so they don't really move around very much. We don't care about cohort B because they're less interesting because all they did was regrow a butt, so we're going to skip it. So conclusion, animals without heads don't move as much as those that have heads. We're all laughing. I just recently got this study accepted for publication, so yeah, what a great one. So why do we care about flatworms? They're evolutionarily significant, super important. They're easily obtainable. They're about $3 a worm. They're expensive, but they're easily obtainable. They're easy to maintain. You shove them in a bowl of water, and as long as you refresh that water every couple of days, they're cruisy. Don't give them metal. Aside from that, they're fine. They're cheap. I said they're expensive, only if you're buying thousands of them, which I did. My supervisor did. I didn't pay for it, so that was fine. They are simple for use in all educational institutions. So we can actually do a lot of pilot studies and really early research in high schools with these because they are so cheap, easily obtainable, easy to keep alive. We can do a lot of baseline studies with that, which is really exciting because a lot of mouse work and fly work is expensive and really hard to keep up. So these guys have that going for them. And lastly, and what I think is most important, they're really fucking adorable. They have those goofy little eye spots, which I just think are the best things ever. They're permanently cross-eyed. I just love them. They're just so cute. And that's it. Thank you for listening.
Wow, what an enthusiastic talk, Shauni. So while we get some maybe house lights so I can actually see when people ask questions, I might ask the very first question. Do all animals require sleep?
So far, yes. So everything we've studied does, and by we I mean the community, does show sleep. We do have some weird little exceptions at certain times of year. So the Alaskan sandpipers, or maybe they're Arctic sandpipers, they go for several weeks without sleep during mating season and migration. But research is coming out that they're actually sleeping on the wing as well as things like albatross. So we're not certain how long they actually go without sleep, but so far, everything needs sleep.
Cool. Do we have any questions? Yep. Did you hear that? Maybe I'll just reiterate for the crowd. So sleep paralysis is really scary. What was the second part of that question? Yeah, does it happen to other things?
Yeah, so that one would be really tricky to answer in other animals. So I don't know if the worms have REM sleep, but in animals that do have REM sleep, it's likely that it could. So a sleep paralysis, so like I said earlier, in REM sleep, your body goes into paralysis so that you don't flail around, get up, drive your car, go get a last glass of water, cook something. Whatever you're dreaming, you don't do. So sleep paralysis is unfortunately what happens when your brain wakes up before your body. So your body is still paralyzed because it thinks it's in REM, but you are slowly waking up. And that's why a lot of people think that there's like a demon sitting on them or a presence next to their bed. It's called like the dead witch in a lot of African cultures because they think that someone's stealing their soul by sitting on their chest. And that heaviness and that presence in the room that you feel is actually just your inability to understand what your body is doing in space. So figuring that out in an animal that can't talk would be quite tricky, but I would say it's likely to occur.
So maybe not so much, I think, therefore I am.
Yeah.
Does anyone else have any other questions? We've got some questions at the back. Go.
Hey, Scott. You look really excited when you talk about
You did.
Is there any research about how many times
So is there a limit on how much you can chop a flatworm up?
There is. This is a really fun study to come across, and it would have been so tedious to do because flatworms kind of feel like congealed gravy or snot. They don't have like it's hard to touch them. They sort of escape away from you. So cutting them is actually really quite tricky. You can actually cut a single flatworm into 172 pieces, and then you get 172 flatworms.
Where did you buy so many?
Another great question. Why did you have to buy so many when you can just chop them all up?
I was very impatient. I didn't want to wait for them to grow.
Shauni, these ones that regrow, can you keep chopping them up? Is there just an endless supply of flatworms?
Yeah, so they're genetically immortal, so they can just go on forever and ever as long as you keep cutting them. The implications of what they've experienced in their lifetime versus like a fresh flatworm, I don't know, which is actually why I bought new ones, because I wasn't sure if I drugged one, cut it in half, let it grow again, if that drug would still be circulating and any side effects.
Or if it would remember you cutting it.
Also that, yeah.
Do we have any other questions? Yep.
Putting the psychology of animals aside, has there been any, did you notice anything if you cut like a flatworm's butt off and it grew a new brain? Did they have the same personality traits, particular tricks that remember it, anything like that?
Excellent question. If
Yeah.
a butt regrew a brain, does it have the same personality as its former self?
So this was actually the point of my regeneration study, but it was very hard to run stats on it because at what point is it a new individual? So it was a nightmare. My poor statistician cried when I explained it to her. It's pretty damn close. So we measured their individual circadian rhythms, and the worms that regrew their brain, the timing of activity was the exact same, but the level of activity was decreased. So which could be something to do with they were fasted as well, so it could be an energy level. But yeah, they were pretty damn close to being behaviourally identical.
I think we've got time for one more quick question. Got a burning question over here. How long does it take to regrow a butt?
About 2 weeks at 19 degrees. So I kept them in a very controlled temperature. If you increase the temperature, they will grow faster. I don't know why I didn't. I can't remember. There was a reason why I didn't go up to 21 degrees, but at 19 degrees, they take about 12 days, and I waited 16 just to make sure that their brains had fully regenerated.
Super cool. So Shauni will be sticking around. So I know that there's other questions and other hands that went up. So you'll have to catch her at the bar when she gets her third drink. But if you just join me in thanking Shauni for her amazing, enthusiastic talk.